Yeah, partly than this, but we start again, and then go to it. Excess carriers. And semiconductors, in particular, we said we are using the transport essentially because of these excess carriers. You have extra carriers which under electricity or under radiance actually move, creating different electrons. So now start looking for it once again. Let's say this is our diameter, and I shown the beam of photons with energy Hd, which are the wavelengths lambda is inside energy Hd by lambda. So for a particular wavelength, whatever this light has, photons have, I take first case and I say this H nu is greater than Eg is the bandgap, and we say that if H nu is larger than G, we would like to see what happens. But first take any other material. Let's say this is your material and you are shining light. So you see, you are seeing some material pass light, some do not, some are opaque, some do pass what is called sunlight or translucence. So the optics says that it's a property of the glass or property of the material in which light is infinite. Essentially what I say, if this has an intensity I, which is anything here, the intensity of photon which may come may not be same as light. It is also possible in some crystals that the wavelength which it will come out may not be same as the initial wavelength also. It also is possible. And at least even in the first case, if you look at same wavelength light appears, the intensity certainly will not be same. Which means this material absorbs photons. This material absorbs photons. And not necessarily, but depends on the thickness and the material property. Not all will be absorbed. So the concentration of the intensity or the light intensity initially very high may due to the absorption be reduced down to some value, and when it comes out it reduces to that value. And the property which is essentially the material, because how much absorption it can give to decide how much intensity light is. So it's not just that in semiconductor is what will happen in any material. This problem will be seen that intensity which is here may not be here same, and let's say some cases may not be the same wavelength. So if taking this into this effect, we can look into this simply. Energy of photons is larger than the band gap. Obviously, it's most likely, and right now let's assume there are no carriers in the conduction band, then a hole which is bound electron here may actually jump to energy h nu. This is say h nu, creating an electron here and hole here. So we say whenever photons strike, depends on the absorption they have, and if the energy is absorbed, obviously some of the carriers may, holes may get, electrons in valence band get excited, and they may create electron hole there. But the electron which is received there has an energy of h nu, is that clear? But according to our theory of semiconductors, for that matter any material, the electrons will not remain at the highest energy, they will try to occupy lowest energy state if it is available to you. In that case, let's say it is available at EC, so electrons will actually come down from its higher energy to a lower energy because it tries to occupy the lowest energy state, which is the law of thermodynamics, it says so. Second law of thermodynamics says so that the entropy has to be minimized so that the level at which energy is equipartition must come there. Now, if that is the theory, then we say, okay, electrons have come here, and let us say you remove h nu. Okay, some electrons gone, but we are looking only one electron for the case, and it has already lost some energy. Okay, and it has come to conduction. It is also possible that this electron which is there, and since there is no way it remains there permanently, because there is no reason why it should remain in the conduction band if there is no force being applied on it. Okay. So it is likely, and that's the probability, these electrons may fall back to the valence band and then recombine with the holes, and we are back to the square one. So there are few processes have taken place. The first process is called generation. So in the first case, when you shine h nu greater than Eg, the electron hole pairs are generated. So the process is generation. The second is relaxation. The higher energy electrons fall to the lowest energy state, they relax, they lose energy. And finally, they may actually fall back to the valence band, and this, as I say, is generation term. So this term essentially called recombination term. So there are three processes we are going through: generation, relaxation and recombinations. So whenever excess carriers are generated by any such optical energy, or for even heat can do that, such electron hole pairs may be formed, but will try to go to which state they will like to go to? Thermal equilibrium number. Because you have got more than Ni were always there. You have got more than that, but system doesn't like to remain in non-equilibrium. If you are removing light, system should go back to thermal equilibrium. So the carriers come back, whatever excess you said, and they will remain, again you will become material intrinsic or n-type or p-type, whichever is the material, it will come back to its original thermal equilibrium value. This is essentially why you cannot see large number of generation of electrons even in thermal case. So otherwise the material is 300 degree Kelvin, 27 degree centigrade may give sufficient kT for you, or not sufficient in fact, 0.025 eV. This is 1.1 EV. I had told you this problem. 1 kT is 0.025 EV and band gap is 1.1 EV. Why electron going there? But there is an issue. Someday before the course ends I'll answer it. Okay, assuming they go there, they keep going then. There is no bar on that. The bar comes from because equilibrium has to be attained, the reverse process actually bring back many of them back to the valence band and recombination starts. So the two processes which are balancing each other is essentially generation and recombination. That brings you thermal equilibrium. So if you disturb the thermal equilibrium, the system will then become in non-equilibrium situation. But then there is a possibility that the rate with which generation occurs and rate with which recombination occurs may have some fixed values. Okay. So what may happen? There may be some generation going on additionally over recombination. Let's say generation is higher than recombination. So some may remain still in conduction band, they may not recombine, but that number may remain constant because generation recombination is trying to balance at a given time, the number is fixed. Is that clear? If you see for a long time and the system has to return to thermal equilibrium, this whatever excess you have created will finally fall back to thermal equilibrium. This is essentially what we call steady state, in which we say the system is time invariant. Though you are actually shining process is time dependent. But after a while we may say whatever is generated partly is lost. So a system remains in pseudo-equilibrium or quasi-equilibrium. Is that correct? Though it is not in equilibrium because it's not thermal, you have applied energy. However, system remains from an outsider as if it's constant. I gave an example that day. You have a pipe in which water is entering. The water has a flow. There is a flow rate, velocity with which water is entering. But after a while, if you see a pipe, you see as if the water is steady there. Essentially, the rate at which it was entering, the rate at which it has come out. You say steady state has maintained there. So steady state is not time, in the sense it's a time system, but variation with time is zero. Is that correct? This is relevant for all our device property, device theory. So we will apply biases, we will apply some light, we will apply something. So system will get non-equilibrium. But it may reach a steady state in which the time invariant part we can actually say equal to zero. Is that correct? However, during this, when this time invariance is not there, we like to see what happens, how the carriers may decay with time. Because you want to reach to equilibrium, but how much is the time taken to do this must be related to rate with which generation recombination is taking place. Is that correct? So this is what we say excess carrier theory which we want to generate. We want to know how many carriers are generated, how many carriers recombine, what is the way they will recombine, what is the time they will take to recombine. Let's look up any situation. If you are a larger number and you are a smaller number, which process will immediately try to help you? Diffusion, because it doesn't like non-equilibrium situation. So there are many processes which are actually helping you. Is that clear? To bring back equilibrium status. Now this is another issue. That means the rate with which recombination generation is happening has also something to do with the process of diffusion if numbers are changing. Is that correct? And so we want to know this relationship with so-called this time business with the diffusion itself. Is that clear? This essentially what we are going to calculate little later is called continuity equation. That is our major interest, to know how much carriers actually will flow at a given this when the gradients are created by, not by us, but by shining. Okay. So if the gradients are created, diffusion will start. Is that correct? This processes which we are essentially want to correlate the process of recombination generation with the theory of diffusion, which we already seen now. This essentially is required because in real life I may pump the electrons or holes by some other technique as well, but then system has to get back to equilibrium and diffusion must help us out. Is that clear? So this, now few things you must know. So I am talking of some time derivative system, dn by dt or dp by dt, but I am also talking as if carriers are diffusing in lengths. Carriers diffuse means they will move in the length. So there is something, space-time relationship is what we are looking into, okay, and to preempt that value which I am really going to get for you is diffusivity of electrons or holes is essentially dn tau n is ln square, or similarly for holes. We are going to try to get this relation. dn is the diffusion constant for electrons, tau is the lifetime. Now what is the word lifetime? We say we like to see before they recombine how much characteristic time it has. When they are decaying, they will decay some characteristic time, that we call as its lifetime. So d into tau, tau is time dependent term, diffusivity is also time dependent, centimeter square per second, and therefore it has a unit of length square, and therefore the length and diffusion which is now coming is getting related to time terms, and this is what we are really looking at. Is that clear? So why I showed you this expression, when I derive that, I want to tell you why I am doing all this, because then I want to relate, if I pump an electron across some point during timing, steady state may achieve, but carriers will move, and if carriers move, how do they profile? How do they do? Because if I know the profile, what do I get? If I know the variation of holes or electrons along the x, what do I get? dn by dx or dp by dx, and therefore which currents? The diffusion current. So I want to correlate this process with diffusion currents. Is that clear? So this all this big talk I gave you just to give you a preamble to what I am deriving, because I want to derive this relationship so that I can correlate timing essentially with the space part. Okay, just for the sake of completeness, if I follow the book, okay, as I say, some things yesterday of course I read some books, so one of them, this part which I am now talking is from Streetman. So we say, if I0 is the intensity striking a material at x is equal to 0, and let's say this is an element dx, okay, so I have to say this value is x plus dx, okay, and this direction is x, then we can say intensity of light in this direction dix by dx. Rate of, as I said, depends on the thickness, how much is dx you are assuming. However, one must say the change in intensity will be proportional to available intensity at x is equal to 0, and as we always do, that is equal to minus alpha times, where alpha is proportionally constant. So what is the solution of this will be? I is equal to I0, yes, e to the power minus alpha x. So what are we trying to say? If the material is very long, x is equal to infinity, how much will be intensity? If x is equal to infinity, that is, this is long enough. Oh yeah. What Ix? But and the boundary condition is that x is equal to 0, I is I0, okay, and at x is equal to infinity, how much is the intensity? The material is very thick, all the intensity will go to 0, which is also obviously seen from there, okay. And at x is equal to 0, I is I0, okay. Thanks. So this means depending on the material, alpha is a material property, it's called absorption coefficient. Alpha is called absorption coefficient. So depending on the material, this alpha may change. So whatever is the thickness, intensity you say, at a distance, depending on the alpha, it will give you some other intensity when it comes out, or at any x you want to evaluate. Is that correct? So let's say if the length is L, instead of this say total length is L, then we say it is e to the power minus alpha L. This is the intensity at a distance L. You can always calculate how much is the intensity within the material. Is that correct? Any point. Is that correct? This is what we are going to use in our all calculation. Okay. So what are we trying to say? If I shine a semiconductor by a optical intensity beam of h nu energy, then the light intensity which will come out of this is essentially because of what? EHP is created because of what? Photons. Because of photons. You will see light outside the material now, and that is function of the initial photons entering the other side. So this is the light which is coming is called luminescence. It's called luminescence. We have seen some devices already in your lab, LEDs. It has luminescence, it shines. So the luminescence is, which kind it is? Since I am shining photons and I am seeing the light at the other side, it's related to photo, so it's called photoluminescence. The first which light you see, you shine light, and the other side you also see a sign. As I say, the wavelength may or may not change, assuming right now no, but it is at least you see wavelengths other side coming, and depending on which formula or how much intensity will be decided by alpha and the distance you are looking for. Is that clear? So the first luminescence which we observe in materials is called photoluminescence. Is that clear? If this material has a property that it actually takes long time to recombine, So what will happen? You will see light after some more time. What is this property called? Phosphorescence. Okay. That is what you see when you go to a many science exhibitions. You stand there for a while, it absorbs the light, and after some time actually image appears there. Okay. That is essentially phosphorescence. So this two things which you have already seen in your second 11th test, every standard, the reason is obviously the light gets absorbed and partly it is transmitted out. Now this luminescence is observed because of excitation of photon beam, we call it photoluminescence. Photoluminescence. The spelling is too tough. Due to photon excitation. So excitation is photon. Instead of photon beam, what actually photon was giving? Energy. Energy can be given by anything. So let's say I have an electron beam, okay, which is excited because electron has energy. If I shine electron beam, those electrons will interact with the valence electrons and still may create electron hole pair. They may still recombine, and you will see the light now coming because of excitation of what kind? Electron beam shining. So if you see a luminescence due to electron beam shining, it is called, what is it called? Cathodoluminescence. Due to electron beam shining. Excitation. Instead of electron beam, let's say I inject, there is a material, I inject constant current. That is, I inject current inside this. Okay. So the third possibility, there is a what is called electroluminescence. It is due to current excitation. So there are three possible luminescence you may see, one due to photon excitation, the other due to electron beam excitation, and third is due to, in the case of old cathode ray tube, which some of you, our old scope still has, some have now LCD screens. So what luminescence you are expecting there? Cathode. There is an electron gun which actually hits the material and you see cathodoluminescence. That's why after some time you used to see that black tube used to get black and no cathodes were emitted enough, so that the picture tube used to be replaced. After nowadays, most of your houses may not have old Sony or other TVs, you may have now LCD, LED. That is just for the heck of it. What is the difference between LCD and LED display? Think of it why I asked you. LED displays are much costlier, at least 1.5 times, 2 times of that of LCD, same size displays. Maybe at the end of the course I'll show you. Actually there is not much a difference. Why they are charging so much is only a fooling people. Of course it has an advantage, but I don't feel the kind of thing they are putting to convert an LCD to LED should be taken. They are charging for the technology which they invented 28 years ago, okay, and still charging you. Okay. So, okay. So is that correct? So now in this, please, there are interesting thing now. Our assumption was in these all luminescence experiments that electrons fall back from the conduction band to the valence band, okay, and recombine. This is called direct recombination. What kind of recombination? Electrons fall from the conduction band to the valence band. Direct recombination. Is that clear? However, In the case of silicon, okay, you never see any light. Okay. This is the issue now. If the electrons fall from conduction band to the valence band, I have not seen silicon LEDs in which light is emitted. Okay. So why it is not emitted? That means there is something more to it in this fall also. Is that clear to you? There is something more to it in the fall. First thing you can understand is silicon and other materials like gallium arsenide, gallium indium arsenide or something, gallium phosphides. These material is different by what? What property? Direct band gap. So if we actually plot their EK diagrams, what is EK essentially tells? Relationship between what and what? Energy and momentum. So if I show this is my conduction band and let's say this is my valence band, okay, E. Then an electrons at the lowest energy state may actually fall at this highest energy state for the valence band, and the energy is essentially the difference between the two called the band gap, because momentum is always conserved. Because with the same momentum it is falling down. Okay. Two things I said you, when process is kinetic, what two things should satisfy? Energy should be conserved, so is the momentum be conserved. Of course there is, all assumptions still elastics, okay, but assume that. There are many issues if we don't take it. This is all this material in which there is a direct band gap, like as I say, the first being gallium arsenide, gallium phosphide and many others. All these materials have a direct band gap. So when the recombination will take place, they will lose energy only. Is that correct? They will satisfy momentum without anything, so they will only lose energy. And energy is expressed in what way? The photon energy. So if I shine or whatever process I do here, and if I see here, then obviously light will come out. Is that correct? So we say whenever there is a direct band gap, emission will be, luminescence will be seen, simply because momentum need not be conserved, self-conserved. However, if you have a material like in silicon, of course it may be different values, but take an example where along the 1-1s or many times 1-0, or some of the values may be along 1-1-0. What does that direction mean? The momentum is different for valence band electrons and that of conduction band electrons. So in most cases when the energy is lost, it is lost in the form of vibrations, and they are called, which particles represent the energy? Phonons. So in the case of all indirect band gap semiconductors, the emission will not be seen photons, it is only phonon, but phonon is not visible. So what you will actually see in the material, vibrations you can't, they don't vibrate with the frequency which is seen by eye. Vibrations when absorbed by the material, what do they give? Heat. So the material becomes heated and it does not show you any luminescence. That's why there is no silicon LEDs. Okay. Of course recently they have come, but some other, that's what I want to tell you why they could be good. Is that correct? So what we say, if I say now, if such materials are to be converted into pseudo direct band gap materials, an indirect band gap material, by making some compound semiconductors or add something which allows me, and here is that theory which I am interested in. Let us say I have an energy level in the band gap. Normally band gap does not have any energy level, but let's say I add something which has an energy level in the band gap, which can be closer to conduction band or maybe closer to valence band, or maybe in the center, wherever. I mean that, like gold has two levels, one closer to the valence band, the other closer to this, but they are found there. That's a very interesting material. So what happens if there is, you add an additional impurity in, which allows you to have an allowed band, these allowed energy level in the band gap. These are called traps. These are called traps. Is that point clear? What is traps? Traps are essentially. Now, what trap was used for what? If there is and the point which I am saying is here is very important. This energy level is such that its k vector is long enough. In the sense, this level translates into many k values. Is that correct? That's our assumption. Many materials show so. So we say it is there. In that case, what can happen? I'll show you 4 processes. And if this is, say, let's say called electron trap, the electrons may first fall to this trap. And let us say then, if the k has larger value, when the electrons then fall to the valence band, may show you light. If the trap level does not have all k vectors possible, then it will still not show you light. It may do 2-step transitions, 2-step recombination. One is from the conduction band to the trap level, and from trap level to the valence band. But let us say by making some interesting material inside, the trap is such that it has energy level which has all k possibilities. This is what we did when we created silicon device which emits light. With which material could do this? Nitrogen, if bonded, if nitrogen binding is not very easy every time, if bonded, can give a level which is what I am now showing. So silicon with some kind of nitrogen plus some precursor you require further, more details some other day. Then there is a possibility silicon devices showing light. What will be the wavelength of the light coming? The energy with which it will fall. So Eg minus Et will be the energy for which light may be seen. So if I can adjust Et values, okay, then I may get wavelengths of different, if there is a direct recombination going on where momentum is satisfied, then you may see a light of this new energies. Okay. This is what we are essentially doing in creating silicon, what we call LEDs if possible. Some of them we succeed, some of them we don't. Okay. So one catch you must remember, since the emitted light has something to do with this energy through which recombination takes place, the wavelength is related to that, the light which is coming out. Is that correct? Eg is equal to Sc by lambda. So the wavelength of light is Sc by Eg. So if I want a yellow color, if I want a red color or this, I must find what I should look for. Correspondingly a material whose Eg is for that wavelength. So the question was asked, and you should also ask, if you go to a devices lab or circuit lab, you use LEDs. So what's so wrong if I paint it by yellow or paint it by red? Why you say LEDs are red LEDs, yellow LEDs or green LEDs, but not blue LEDs, which now came very recently? The reason is to get an EG of your choice is not very, this is called band gap engineering, and if you can do some band gap engineering with K infinite possibilities, then you may get different colored lights coming out of even silicon, indirect band gaps. Is that clear to you? This situation is called essentially newer optical devices which are coming are essentially governed by this engineering called band gap engineering. So there is another area of devices which is more related to optics or related to what we call optoelectronics or photonics as the new word. Jargon mein rehna. In my time I used to call optoelectronics, so log haste. Photonics, now it's a big name, okay, big money, big name. So any proposal I make to government or anyone, I must not write I am looking for electroluminescence. I should say it has a photonic material which has a photonic band gap, something same thing in a different way I say. सामने वालों को आता नहीं है, उनको ये नाम सिर्फ गूगल से पता लगते हैं. They give money to you. Okay, that's how the projects are essentially attained. Okay, so is that point clear? So the direct band gap, indirect band gap materials, and there are essentially the cause of different light coming out of it. And in normal case, what we are saying that the recombination process is essentially through a trap, then it is called trap assisted recombination. What is it called? Trap assisted recombinations. Trap is allowed energy state. In a band gap. So there are possibilities that there will be a direct recombination possible, but there may be, if there is no direct possibility, let's say Eg is too high or let's say Eg is too small, depends on either case, the recombination may still take place through trap, and traps are always present by some way or the other, whether you like the or you don't like, there will be always traps present. How many kinds of traps do you believe we can have? Trap is essentially where electron or hole can actually reach that state. Okay. Probability of electron reaching to a trap level will be highest when where the trap level should be near the conduction band. It's more likely hole may be trapped if the valence band, trap is closer to valence band. Now the question arises, if electron has to be captured by the trap, what kind of trap it should be? It should be neutral. That means it has no charge of itself. So whenever it will receive an electrons, it will become negatively charged. Is that clear? Similarly in the hole, what kind of this should be? It should be actually negatively charged there. When the hole reaches there, it neutralizes it. Is that correct? The trap level for a hole is the one when a negative charge trap near the valence band picks up a hole, because otherwise hole coming up there is very unlikely, or this electron falling down is essentially hole coming up. So that hole trap is normally negatively charged, electron traps is normally neutral. Is that clear? This is how we say traps are neutral or charged traps, is what we look in. Electron accepted, then it becomes negatively charged trap. Holes accepted, it becomes neutral trap. Okay, charge will be actually removed from there. Is that point clear to you? So this traps are also depends on now what we'll see. The trapping will be, we'll see derive that expression later. Trapping will be proportional to how many things? Firstly, how many carriers you have? इतने आ सकते हैं, उसके proportional होगा. Then it will be proportional to probability of this ET के ऊपर कितने probable है वहाँ पर carriers trap होने का, तो distribution function लगा हुआ है. And then how many traps are actually density है उसकी? So it depends on actually trap density. It also depends on the probability of occupation, and it also depends on the number of available carriers, and it also depends on some interesting constant, which is proportionality constant. We say that if the carrier, let's say this is a sphere and this is trying to capture, okay. Let's say this is a circle and a carrier is coming and to be trapped. So the area, which is called divergence as we say, area in which it can be captured is called cross-sectional area. It may be spherical, but the section which it sees where it can be captured is called as cross-sectional area. So trap density, cross-sectional of the traps, the probability of occupation, and the available carriers where they can be trapped, all this will decide the recombination term R, how much recombination. Is that clear? Is that one clear? Through the trap, R will be proportional to how many things? The cross-sectional area. Larger the area, obviously they will more likely to be trapped. Smaller the area, less cross-section means they may pass through or sideways. So larger area means larger trap cross-section. So number of traps, number of possibility of occupation where trapping can happen due to distribution, then the cross-sectional area and the available carriers only can be trapped. If there are no, n is very small, how many? Only those many can be trapped. Nt may be infinite, but n is 10, so only 10 can be trapped. So proportional to all this, so recombination term has many interesting features. I would like to see how much actually is the recombination. So whenever carrier comes, it has an electric field and it is going to be trapped. Okay. So what your model is, whenever electron is capturing, it has an electric field sphere around it, where it is trapped actually gives any direction, because one cannot say which direction electron is going to come. So there is a sphere of influence where electron will be absorbed. Okay. Now if I am seeing electron coming from here and this is the sphere, so the area which this electron sees is the cross-sectional area of the sphere as if I cut it. Any electron which hits this surface will be absorbed. Correct. So essentially imaginary, but that number has something to do with the property of the trapped material. How many, what the influence field it can create is a property that we express in terms of equivalent cross-sectional area. Is that clear? The fictitious may be, but it is something related to that material. This is that's why they say proportionally constant, which essentially says as if it is proportional to area where it can be easily captured. But material, because the charge on every material inside a lattice will be different. Like six group element will have 2 electrons put there, 3 may have 1 less. So it depends on what material is around, the electron capture will be different. Is that clear to you? This is what the transport we are all three are talking now, that electrons are actually influenced by the electric field through when it moves through a lattice. This is another way of looking. Okay. So having said this, that traps can also assist you to recombination. We'll derive that expression afterwards. But let's remember there can be direct recombination or there can be trap assisted recombination. So we say either way the recombination will take place. Generation could be either through photo, electron beam, current, even thermal, that is what natural is. So any process can generate, but the recombination could be either of these and they will recombine. And what is the purpose of recombination? Otherwise the generating term will keep making it infinite. Okay, so it must be balanced to bring the system back to equilibrium. So let's start some more calculation on time. Let us say they call Gn as generation rate as we call for electrons, and Gp, some write capital also you can write, it really depends on generation rate for holes. In normal case, one assumes, and many cases, at least in silicon it is valid, Gn is equal to Gp. But this is not 100% true for all materials and all semiconductors. Okay. So in that case, for electrons you must use different G, and for holes you should use different G. As of now, we will assume this. Let us say initial carrier concentration, let's say I have a semiconductor bar. Okay, let's write this. Okay, before we quit this, if Hν would have been less than Eg, what would have happened? It would have just absorbed. Okay, Hν would have, you are shining light. It cannot excite whole electrons, so it will be absorbed and mostly it will form heat. Okay, it will form heat. So if you keep shining the light, which has lowered this energy, it will keep heating the material. That's what most people we do when we say optical heaters or light heaters. Okay? It just shine light on them, okay, of that wavelength which is not coming out, so no luminescence, so it heats. Okay. So let us say I have a material which has concentration of N0 and I am shining light, okay, and it creates whole electron pairs. So we say N0 plus excess carriers, they delta n and delta p are the EHPs. Okay, delta n is the excess carriers. The new concentration will be equal whatever your thermal equilibrium value plus whatever is excited by the light. Please remember this carriers what I said, because I say if it is whole electron pair, excess electrons must be equal to excess EHP, whole electron pair, so it will always be equal to this. If it is a p-type material, since there are some n0, how much will be holes? Ni square by n0. So new P now will be P0 plus delta P or delta N also. And then we may replace delta N by delta. So holes concentration increased by delta P or same as delta N. Electron concentration has increased from its equilibrium value N0 by delta. Now our first assumption in solving is, why I put this delta? What does that mean? N0 is, compared to N0, this number is smaller. If this number is larger, N0, P0 will not have any influence, they themselves will decide the carrier concentration. If delta N is twice N0 or thrice N0, it is that number which you are going to talk. But essentially we say the recombination will not allow that much, so we say delta N essentially is less than N0. Please remember, I keep saying I will replace delta N and delta P. Now take a case, how much is the change? And that's very important for us, because that will tell us which carriers are relevant for us. An example, number wise, maybe I'll give you to you that number before I do further calculations. I have chosen a P semiconductor. Let's say P0 is 10, okay, to make it point clear, 2 10 to the power 16 per cc. Why this number? 1.5 square. So N0 is Ni square by P0, which is 10 to the power 4 per cc. Okay, is that clear? N0, P material, N0 is very small, P0 is very large given to us. And let us say I shine light and number of carriers delta N equal to delta P is 10 to the power 14 per cc. The electron hole pairs which are generated due to the shining of H nu is 10 to the power 14 per cc. So how much is N? Sorry, how much is P now? 2.25 into 10 to the power 16 plus 10 to the power 14 per cc, of course, and which essentially means, this is, if I make 16, so this is 0.01 into 10 to the power 16. If I add, this becomes 2.26 into 10 to the power 16 per cc. But what happens to N? What happens to N then? N is equal to N0 plus delta N, 10 to the power 4 plus 10 to the power 14, which is 10 to the power 14 per cc. So in a p-type material, which carriers are really have become large enough now? Electrons. What has happened to p-type? Practically very small change. 10 to the power 16, 2.25 became 2.26. Whereas electron concentation was 10 to the power 4, now it has reached 10 to the power 14. Is that correct? So which carriers have now dominance? The minority carriers, the electrons which are minority in P have become now dominant carriers, because change in P is very small compared to change in N. Is that correct? So the change in N, which is for minority carriers in P-type, is becoming some important quantity now. Is that clear? P is not changing very much, but N is changing drastically. So if any phenomena when you recombine them will happen, it is this electron recombination which will start as a dominating effect for you. Is that clear? And that essentially means that minority carriers become very, very important in non-equilibrium situations. Is that word clear? When I keep saying earlier why minority carriers are dominant in process of transports, because that number may change, which may have more influence than the change in the majority carriers. And that therefore we say minority carrier transport is, in most bipolar devices I say, will be more dominant effect than in the case of mass, where we say okay, it's only drift. Okay? We'll come back to that. So this fact that the number changes drastically for the minority carriers is the crux of all the work which we do. Is that clear? Is the crux. Now calculate. Okay, this number, this is only a calculation, so there is nothing more about it. This is part of the way numbers you will like to see. Okay, so I already written that relationship. Let us say this has time dependent term. At any time t when the light was shining, Nt will be equal to N0 is constant, that is a thermal equilibrium value, so N0 plus delta Nt, this. Now we are interested in the net change of electron concentration. So we say T by dt. Okay. Where the rate change of electron concentration will be proportional to what? The change in actual available concentration. So how much was initial concentration in normal case? Sorry, proportional to. In thermal equilibrium it was Ni square minus Nt. How much is new carrier concentration? Nt and Pt. Is that correct? So therefore, it's proportional to available electrons, proportional to available holes. So it is Nt-Pt into alpha is the rate change occurring because of this. But what was initial thermal generation rate? Proportional to Ni square. So what is the difference from the thermally generated to optically generated? The difference is the carriers which can decay. What is the Nt actually we are talking? It is essentially the excess carriers, because N0 is fixed. When I differentiate, that goes anyway. So I can even replace this later, and this constant dNt by dt is given a constant, recombination constant alpha r, okay, Ni square. And what should I write now? Nt-Pt. Let's write this expression for Nt-Pt. N0 plus delta N. I won't put T here, just it is always there. P0 plus delta N, or maybe right now if you wish, delta P alpha R Ni square N0 P0 plus delta N P0 plus delta P N0 plus delta N delta, all are minus. So which term cancels here? This and this. Will N0 P square and thermal equilibrium, they cancel. If delta N is small, though we are assumed it is larger, okay, the square of delta N in delta P is also smaller. That's what the number proportion to the normalized value. So we actually need this. If delta N equal to delta P, then it is alpha R, sorry, minus alpha R delta N N0 plus P0. Is that okay? N0 plus P, delta N is same as delta P. So delta N into N0 plus P0, minus sign is taken out. However, we also said how much is N0 P0 related. Normally in N-type semiconductor or P-type semiconductor, one of them will dominate. Then we will say this is minus alpha R. Please remember, If it is a p-type semiconductor, p0 will dominate. Is that clear? In the n-type semiconductor, holes dominate. In a p-type semiconductor, electrons will dominate. And which carriers we are talking here? In a p-type semiconductor, this was material for p-type. Which carriers decay I was more interested in? Minority. Which are minority in p-type? Electron. So I am looking for electron which is minorities in p-type. So I say p0 is larger than n0 because it's a p-type material. So I neglect in terms of this. So I get minus alpha p0 into delta n. Now this equation, how do we solve such simple equation, differential equation? What is the solution? Yes? Okay, let me first keep it. So d and t can be also written as delta nt by dt. dn by dt can also be written as, because n0 plus delta n, n0 is constant, so dn0 by dt is 0. So that is equal to minus alpha r p0 delta n. We define a term tau n0 as alpha r p0. Alpha as a unit such that 1 upon alpha r p0 has a unit of time, in which case this equation d delta nt by dt equal to minus delta n by tau n0. Is that correct? This tau n0 is called minority carrier lifetime, which is why called minority here, because electrons are in minority. It is electrons which are minority, the carrier lifetime. What is the lifetime word should be used for? The time, average time taken before electron recombines. It's like its lifetime, how long it will survive. So if you define this, what is the solution of this? Quickly. Delta nt is equal to how much? Minus है भाई, जल्दी जल्दी बोलो. Just for the heck of it, if it would have been n-type semiconductor, what equation I would have got? d delta pt by dt is equal to minus tau p0 delta p. And how much will be tau p0 there? 1 upon alpha r. If the material is other kind, holes would have been in the minority and equivalent equation could be written for the same case. Yes, solution क्या है बोलो ना, इतना simple differential equation है. तो भाई इसके लिए कुछ तो initial condition चाहिए ना. So at t is equal to 0, we call this number delta n at 0 is delta n, fixed value. Is that correct? Delta n. In that case, the solution will become, yes, delta n is equal to capital delta n e to the power minus t by tau n. Okay? If that is the initial condition, t is equal to 0, the carrier concentration is delta n. How does it look if I plot it? How will I look this expression? If I plot excess carriers concentration, delta n or delta p, whichever I draw, okay, call it this. This is my, which was this material? P type. So this was P0, this was N0. Let us say this number is delta n. And how will it decay? Exponentially they will start decaying with, okay, this side is P0 is only this much. Delta n will be same as delta P for the T is equal to, so their decay is so there is hardly any real decay happening for P holes because the material is P kind. But what is strongly decaying and where it will go to which value? It will go to its equilibrium value, and sometimes we define this value as NP0. What does this NP0 means? Electrons in P at thermal equilibrium. Is that correct? Electron in P at thermal N0 is same, but NP0 may be more relevant because we say electrons in minor. Is that what here? Electrons are minority in P. So we say NP0 is the equilibrium carrier concentration of electrons in P semiconductor. By same argument, it will be PN0, minority hole concentration in N material at equilibrium. Is that so? Books actually keep changing this. So I just thought if you see other book, they may have written instead of N0 NP0, which is essentially same. So this decay which you obtain essentially now says that depends on what is the tau n0 by maths. Wherever this 66% of the value, wherever this decay will occur 66%, that is called characteristic time, and that time we defined as minority carrier lifetime. If it is larger, what will happen? If the carrier lifetime is very high. So what does that mean? This will take long time before it will go to equilibrium concentration. If the minority carrier lifetime is very small, very small, it may actually decay as fast. This is very relevant. Whether we want to keep electrons or minority carriers for longer time in particular regions or a shorter time depends on what we are actually looking from the device. For example, a transistor, if you want it to actually have a higher gain, okay, we may say the electron lifetime in NPN transistor in P base should be large enough. If the lifetime of electrons in the P base is large enough, we can show you later that the gain beta will be very high. However, since it is long enough, it will move very slowly as if, and therefore what will it do? If you are looking for a change of positive to negative, it will take long time before it will recombine. So the device will become slower in its switching operation. So अभी दो चीजें समझ में आई. Lifetime has two influence. One on the gain, the other is on speed. So high speed करना है तो क्या करना चाहिए? Lifetime कम करो. तो lifetime कम किया तो gain भी कम हो गया. तो क्या चाहते हैं? इसको बोलते हैं डिजाइन. What do you really need? If you are looking for high speed circuits, थोड़ा low power पे रहो. Okay. Low पे रहो. Otherwise it cannot sustain. Okay. So think of it, what essentially you are going to do when the device is. So this is very important parameter.